Yeah, thank you, Mr. Chairman, for this kind introduction. So the topic is studies on the stress dependence on flexible integrated capacitive pressure sensor for minimal invasive biomedical applications, and I'm presenting this talk on behalf of my colleague Jutta Müntjes. So first of all, let me say some words about the motivation. So we're talking about capacitive-based pressure sensors, and why do we want to use those sensors? Like for medicine or medical application, it's very important to measure some pressures of body fluids. For example, the pressure of blood, intracranial or bladder pressure. And that's because when in the body the pressure is not well adjusted. For example, if you're to a high pressure, too low pressure, this means that the patient is harmed or harm is caused by this high or low pressure. For example, in the blood, when the pressure is too high, you can suffer heart attacks or strokes or blood clots. And if it's too low, you have a problem, for example, dizziness or in an extreme case also organ failure. So for this, it's very important to measure these pressures. You can measure these pressures via invasive methods like a catheter, and this is necessary. For example, in the case of intracranial pressure, you have to go inside the skull, and when you go inside the skull, you need a catheter. And for blood pressure, it's a different reason. When you go to the doctors, there's other methods and non-invasive methods to measure the blood pressure. But they're only punctual on time, so they measure it once a day or so. And so it's very difficult to get measurements all around 24/7. And for this reason, it's better to make an invasive system. For example, this system here shown. You see the sensor tip here, which is put into the femoral artery, and this connected via wire to a transponder unit. And this transponder unit can be read out, and so you can get a 24/7 measurement of the blood pressure, and that's really important for patients where the reaction on the drug treatment used to adjust the pressure is not really well. So when you make such a system, you need minimal interference, which is crucial, because when you have too much interference, you have resistance in the vessel, and so what we want to make is a small system which leads to less discomfort for the patient and a decreased flow resistance in the vessel. So another reason is we want to make it so small or thin so that it becomes flexible. So we want to make a flexible sensor, which also means when it's flexible, you can get into regions or places where you can't get before, because when it's flexible, you can bend, and so you can reach very small vessels. But when we make a flexible sensor, the bending dependence of the signal is, of course, important. So the sensor we use is here a capacitive pressure sensor made by the Fraunhofer Institute for Microelectronics Circuited Systems in Duisburg, Germany. And this sensor was made or developed for the system shown before. So what we have here is pressure sensing regions. So that are sensor membranes, readout electronics, and bond pads. The sensor overall is 5.6 millimeters long and 0.7 millimeters in width. And here you see the sensor membranes. They are around 110 microns wide, and there we have 24 membranes designed for the pressure measurement and 24 membranes for the temperature compensation. The measurement range of the sensor is between 900 and 1,400 millibars. This pressure is necessary for measuring blood pressure, and we have a temperature range between 15 and 45 degrees Celsius, and this is also for measurement in the human body. So for the measurement, we have a 4-point bending setup, like this shown here. So we have 2 supports on the lower side. We have placed the sensor in the middle, and we press with 2 aluminum bars from the upper side downwards. So then we place this pressure sensing region here between those 2 bars, and that's because then we have a nearly constant stress distribution due to the constant bending rate as shown here. So here in the middle between the 2 bars we have a constant stress distribution, and then we make a measurement of pressure sensors with different thicknesses, so that we can evaluate the influence of the sensor thickness on the sensor signal when we bend it. So for the bending, definition is the displacement W we used. So the displacement W is the difference between the sensor or the position of the sensor in the unbent state, which is here, and in the bent state, which is shown here. So for the assembly of the sensor, we have thin silicon sensor with thin by lapping and polishing to thickness between 20 and 60 micrometers. And we have made a flexible polar-based cable with electroplated gold pads. This was made in-house, and we used anisotropic conductive adhesive as a connection method because when we use flip chip bonding with stud bumps, or for example ball edge wire bonding, we could damage a small and fragile or thin and fragile sensor. So connection works as follows. We have here a temperature chuck, place the sensor on top, place the adhesive on top of the sensor pad, and connect the flexible cable by the application of pressure and temperature. Then the result, what we get is this. You see the sensor down here, and this is a polyimide cable, and here you see the connection between the cable and the sensor. And what's important is that we have a flexible connection. That means that the influence of the cable on the sensor during the bending measurements is low, so that we don't influence our measurements with that. For the simulation, we have made a finite element program in the simulation, and the model is shown here. We have a lower electrode at substrate, it's a silicon. We have a silicon nitride insulation layer between, and polysilicon membrane is the upper electrode. And here you see the gap for the membrane is the 0.8 micrometers vacuum gap. For this, the simulation of the circular parallel plate capacitor alone, we could use the point symmetric setup because of the rotational symmetry. But when we simulated the beam, the whole beam, and the sensor cell on the beam, we could only use the axis symmetric setup. So for the results, we simulated silicon bars of different thicknesses. So that's shown here. We see here the position in micrometers, so that here is the upper aluminum bar on position 0, and this is the middle of the setup. And you see that depending on the different thicknesses, the stress is nearly constant over the whole range. And what you see is if the thickness is higher for the same displacement W, we get higher stresses in the surface. So what we did then is here the simulation of a single capacitor under ambient pressure, so just the membrane without any bending, and so we see here under certain ambient pressure the displacement of the sensor membrane, and we get parabolic capacitance change depending on the ambient pressure. So okay, the capacitance changes or rises like a parabol with increasing ambient pressure. So for the simulation, next step was we combined the two simulations before. So that means we have a pressure sensing membrane, so as on the slide before, and now we add additionally the bending of the substrate. So this substrate is bent, and it's bent in a compressive way. That means so that this side goes up, and this side goes up, and this side goes down, so that the sensor membrane is compressed. And this leads to a certain effect, and that effect is shown here. So this is a displacement, the displacement W I've defined before, and we see when we bend the sensor signal changes, and we see that it rises. So this is caused by a decrease of the decrease of the vacuum gap. So the sensor membrane comes closer to the substrate, and so the capacitance increases, and we see that here. And this is the same effect as if the ambient pressure would be increased. So there we have a cross dependence between the bending, of course, and the ambient pressure, or what's measured. And what you see here is that the maximum capacitance is reached without increasing ambient pressure. So that means normally when you increase the ambient pressure, there exists a certain point where the minimum distance between the membrane and the substrate is reached. And this can not only be achieved by increasing the ambient pressure, but also by bending the sensor. And what was also seen in the simulation that when we have a thicker substrate with the same, we see this early attachment of the flexible membrane to the silicon substrate. So this can be seen here. So here's the sensor membrane under compressive strips, like here. So the membranes are on the top side when we are pushing here. So this is a curvature. And this means the membranes are compressed. And this are the measurement results, the real experimental results. And we see here the results for 3 different thicknesses of the sensor. This is here 50 micron, 44 microns, and 21 microns. And we see, first of all, nearly parabolic shape of this dependence on the displacement, or of the measured value on the displacement. And the second thing we see is what we have seen in the simulation, that we reach a maximum value, and this maximum value is reached earlier for thicker sensors. So this is a 15 micron, and this is a 21 micron. For the tensor stress, we see the situation here. So we've turned the sensor around so that the membranes are on the lower side, and in this case, the bending counteracts the ambient pressure. So this means we increase the stress in the sensor membrane, and this increased stress in the sensor membrane counteracts the ambient pressure, which tries to push the sensor membrane downwards. So what we see here is a decrease of the measured result, or of the measurement. So a decrease in capacitance, which means an increase in distance between the sensor membrane and the substrate. And also what we see here is that the dependence on the bending is greater here for the thicker sensors than for the thinner sensors. So what we did then is we made a fitting of the experiments of the measurement results to a parabolic function. That is that B was shown here before, so that B is this value, and we make a fit on this function shown here. So we fit this parabolic region. And what we look at is this parameter A, the dilation parameter A for different thicknesses, because we see then here that we have a higher dependence of the pressure signals for a higher substrate thickness. So the thickness is shown here on the x-axis, and the dilation, so this parameter A, on the y-axis. We see here that for thin sensors, this dependence, or this dilation parameter A, is smaller than for thicker sensors, and thus we have a less dependence, or a smaller dependence on the bending for thinner sensors. So to come to a conclusion, we have developed a stable process flow for flexible capacitive pressure sensors. We've made a reliable 4-point bending measurement method, so it's a reliable tool to evaluate those sensors. And we successfully fitted the measurement curves to a parabolic function. And next we have to do is additional pressure dependence of the bend flexible sensor has to be examined. So what we didn't do yet is the combination of the bend sensor and an increased ambient pressure. So we did this only at room pressure. Next, the simulation of flexible pressure sensors and 4-point bending setup has been accomplished. So a simulation of pressure dependence is possible, and the prediction of the behavior on the bending is possible, so that we can predict what happens to the sensor membrane in post-addition. And for the future, we have to make quantitative comparisons of simulation and experiments. Thank you for your attention, and if there are any questions, I'll be glad to answer them.